When working with limits and looking at the limit of a function as x approaches a specific numerical value, you're trying to see as you look in towards your x's from the left and the right, infinitely close as you can, what the y's are approaching. And we have a formal definition of a limit, as well as looking at maybe finding those limits graphically or analytically. I've made videos of those types of problems with limits, and they are linked in the description of this one. The focus of this video is to look at what do we mean when we have a limit as x approaches either positive infinity or negative infinity. So here I'm actually looking at what's the function doing as I look forever right for the limit as x approaches positive infinity, or what's happening with the function as my x's are forever left when it says the limit as x approaches negative infinity of a function. So these types of questions with limits are actually the same sort of process, and actually is the same process that we thought of when we were looking at end behavior for graphs. So when you think about the end behavior for polynomial graphs, for linear graphs of linear functions, for graphs of rational functions, you'll see that what you're getting for the limits in the notation with limiting process is what you would have for your end behavior. But there are other functions that you probably hadn't thought about with the end behavior before that you'll be able to extend the information to those once you see a couple of this analytically. So let's get started. Limits at infinity. Now there will be sometimes that people talk about infinite limits as x approaches a value, whether the function is going off into unbounded behavior. Those, really the limits don't exist, but they talk about what manner in which they don't exist. These are limits at infinity, which actually is kind of a misnomer that we're actually looking as the x is toward off to infinity. So again, we're looking at end behavior. Let L be a real number. Two different statements. The first statement is the limit as x approaches infinity of f of x. So as I look forever right in my end behavior, equals L means that for every epsilon greater than 0, epsilon is a small positive number, there exists a capital M greater than 0. So this is where you start to see that if you did the epsilon-delta proofs for limits as x approaches C, a specific number, that formal definition differs than this one in that there exists here a capital M greater than 0, such that the absolute value of f of x minus L, so the output that you get from running that x values through the function minus the limit value, and the absolute value of that is less than epsilon whenever your x is greater than capital M. So here's what we're looking at now. As I have my function and I'm looking at my x's going off to positive infinity, and it looks like my function values are approaching a specific real number, my L, that will be true that if whatever epsilon they give, so let's say we have an epsilon that would be this much distance on our picture, so L plus epsilon, L minus epsilon, and then if I draw that band in, that there'll be some point where after that point all of the x's, so it looks like from this graph that my capital M would be about right here, that any x greater than that, my function stays in that epsilon band. It never comes out of it after that. If someone gives me a different epsilon that's smaller than that, then I would have to look with that new epsilon band how far out I would have to go. So if I had a smaller band, this M wouldn't be enough anymore. I would have to go all the way out to here for my M, so that any x bigger than that M would produce an output of my function that would still be in that new smaller band. So when I'm looking at these limits at infinity, what you have to do for every epsilon greater than 0 is give a far enough out value so that any x after that will produce a function output that will be close enough to your L that the function output minus L's absolute value will be less than epsilon for all of the x's to the extreme of that. Now, what about the limit as x approaches negative infinity of f of x equaling L? It's the same idea, same thought process, it's just as you go forever left. So when we look at this, the limit as x approaches negative infinity of f of x is equal to L means that for every epsilon greater than 0, there exists an n less than 0, because this is forever left, and so my x's are negative when I'm going off to the left, such that my absolute value of f of x minus L is less than epsilon whenever my x is less than n, because again, I'm going off to the left. So here, if this is my limit, and someone gives me an epsilon band of about that much, so L minus epsilon, L plus epsilon, and I think about just carrying this across, then about right here would be that n that's less than 0, so that every x left of that n would produce an output of a function that's closer to that L than my epsilon band, so it gets caught in that epsilon band. If someone gives me a smaller epsilon, then I would have to go further out to get the n, but after that, the function would be caught in there. Now, if we have these as our y equal L horizontal lines, you're really talking about a horizontal asymptote of the function when you have these limits as x approaches infinity of f of x being L, and the limit as x approaches negative infinity of f of x being whatever that limit is. Next up, we're going to look at some specific expressions that we can find the limits of quickly as x approaches infinity or negative infinity, and then look at a process that would help us find these limits analytically instead of looking at them graphically each time. Now, there are a couple limit building blocks that's really important for us to get comfortable with so that we are able to investigate the limits at infinity analytically. And here is one of the key ones. It says let R be a positive rational number. So it's positive, it's got to be greater than 0, and it's rational. So it can't be an irrational value. It has to be something that can be written as a ratio of two integers. And let C be any real number. So C can be any real number at all. Then the limit as x approaches positive infinity of a real number divided by x to a positive rational number. So I have to make sure that I've rewritten it so my exponents are positive in my expression before I try to put this theorem to use. Then a fixed constant numerator divided by x to a positive rational power, limit as x approaches positive infinity, that will go to 0. So here you think about your numerator being fixed and your denominator, if that power on your x is a positive rational number in the denominator, then you're going to have a fixed numerator divided by a denominator that gets bigger and bigger and bigger and bigger and bigger, and so my limit is going to 0. So for example, if I take the limit as x approaches infinity of 5 over x squared, so think, if I am letting x go off to positive infinity, then when I think, say, x is 10, that'd be 5 over 100. But what about if x is 100? That would be 5 over 10,000. And when you think about what's happening with that value of that fraction as x gets bigger and bigger, when you have a constant numerator divided by x to a positive rational exponent, this fraction value is going to 0. Now, we also have to think about what happens when x is going off to negative infinity, and we do have to be careful. Our exponent is a positive rational number, but it has to be an exponent that if I have a value plugged in for my x that's negative when I'm going off to negative infinity, that I can actually evaluate that over the reals. Well, remember, fractional exponents, the denominator of the fractional exponent is the index of your root. And if the index of my root is even, like a square root or a fourth root or a sixth root, etc., then that's not defined over the reals if I take an even index root of a negative number. So I have to put a little bit of a disclaimer in here that I have to have it that x to the r is defined. So I have to be careful not to have a fractional exponent with an even denominator if I'm going for my x's off to negative infinity. But when my fractional exponent is simplified. So, but if x to the r is defined when x is negative, when x is less than 0, then the limit as x approaches negative infinity of a real number divided by x to a positive rational number, again, comes out to be 0. So this would be like the limit as x approaches negative infinity of 5 over the cubed root of x. It's okay for an odd index, or they could even have written that as limit as x approaches negative infinity of 5 over x to the 1/3 power. Means the same thing as this. Odd index, I can take an odd index root of a negative number and have a real answer. So that is defined. And this constant divided by a denominator that gets big, that fraction goes to 0. So let's see how we can utilize this in an actual overall problem of a limit as x approaches either infinity or negative infinity. So here are 4 examples that we're going to look at and think about our properties of limits. So my first one, I have the limit as x approaches infinity of the expression 12 minus 4 over x to the 5th. Now with properties of limit, the limit of a sum or difference is the sum or difference of the limits. And that works with limits going off to infinity or negative infinity as well. So I have the limit as x approaches infinity of 12 minus the limit as x approaches infinity of 4 over x to the 5th. Now I want to evaluate these limits individually. The limit as x approaches infinity of a fixed number 12, well, when we're taking the limit as x approaches whatever of a constant, it's just that constant. So that is 12. Minus, and then the limit as x approaches infinity of 4 over x to the 5th, well, that's a number over x to a positive rational exponent. And so then when I look at that, that's the theorem that we just talked about. And so this limit goes off to 0. And then 12 subtract 0 gives me 12. Let's do the next one. The limit as x approaches negative infinity of 7 plus 2 over x to the 1/3 power. Well, that's the limit as x approaches negative infinity of 7 plus the limit as x approaches negative infinity of 2 over x to the 1/3 power. So the limit as x approaches negative infinity of a number is just that number. And then as x approaches negative infinity, I can take the cubed root of a negative number. So this x to the 1/3 is defined for negative values of x. And I have a real number numerator divided by x to a positive rational exponent as x approaches negative infinity, that limit. So that limit goes to 0. And then 7 plus 0 gives me a limit of 7. I'll try to sneak that in there. Okay, how about the next one? Well, here I have this overall fraction of a polynomial divided by a polynomial. And when I'm trying to evaluate that, what you want to do is you want to look at the highest exponent in the denominator. So look at the highest exponent in the denominator. And to get it where you can evaluate and use our limit properties, we are going to take and divide every term in the numerator and denominator by the highest power of the x in your denominator. So x squared. So I'm going to go 7x squared over x squared minus 4x over x squared plus 1 over x squared. And then it's 2x squared over x squared plus 5 over x squared. Now, I can do this because I'm really just building this fraction top and bottom by 1 over x squared and then distributing it through the different terms. So now when we look at this, I can simplify each of the fractions. That's the limit as x approaches infinity of, well, 7x squared over x squared is 7 minus, and then this will be 4 over x plus 1 over x squared. And that's divided by 2 plus 5 over x squared. Now, applying our properties of limits, the limit of a quotient is the quotient of a limit, and the limit of the terms is the sum or difference of the limits. And as I look at this, going through, I have my fraction bar. In the numerator, the limit as x approaches infinity of 7 is still 7. And then the limit as x approaches infinity of negative 4 over x, well, that's a constant, a real number numerator divided by x to the positive 1 power, and 1 is a positive rational number. So that goes off to 0. And the 1 over x squared limit as x approaches infinity also goes to 0. In the denominator, the limit as x approaches infinity of 2 is 2, and the limit as x approaches infinity of 5 over x squared goes to 0. So our limit for this comes out to be 7 halves. 7 minus 0 plus 0 is 7, 2 plus 0 is 2. How about this next one? So again, look at the highest exponent in your denominator. So this is the limit as x approaches negative infinity of, and I'm going to build the top and bottom by 1 over x to the 5th, because power of 5 is the highest exponent in the denominator. So when we do that, that's 4x cubed over x to the 5th minus 2x over x to the 5th plus 1 over x to the 5th, and then I have 4x to the 5th over x to the 5th plus 2x over x to the 5th. So that gives me the limit as x approaches negative infinity of, my first term now, it's 4x cubed over x to the 5th. So when I simplify that fraction, I get 4 over x squared. And then minus, simplifying 2x over x to the 5th is 2 over x to the 4th. Then plus my 1 over x to the 5th. Then in the denominator I have 4, and then plus 2 over x to the 4th. Now once I have that all simplified, I can use my properties of limits. The limit of a quotient is the quotient of the limits, and the limit of a sum or difference is the sum or difference of the limits. So as x approaches negative infinity, all of these are defined, but a real number 4 divided by x squared, so the numerator stays fixed and the denominator gets huge in that fraction, so you have a fixed numerator divided by a real increasingly large denominator, that fraction value goes to 0. The next one also goes to 0. So in my numerator, I have 0 minus 0 plus 0. So my numerator, I have 0. And in my denominator, I have 4 plus 0. And so that's 0 divided by 4, and 0 divided by 4 is 0. So let's look at these examples. Here I have the limit as x approaches infinity of 5x cubed minus x over x squared plus 4. Now it says x approaches infinity, or if it were x approaches negative infinity. So I'm going to look at the highest power in the denominator and divide everything through by that. And really what I'm doing is building the fraction 1 over x squared over 1 over x squared and distributing it through. So this is the limit as x approaches infinity of 5x cubed over x squared minus x over x squared, and then x squared over x squared plus 4 over x squared. Now simplifying that, the limit as x approaches infinity of 5x minus 1 over x over 1 plus 4 over x squared. Now when I look at each of these and see what happens with them, the limit as x approaches infinity of 5 times x, that goes off to infinity, minus the limit as x approaches infinity of 1 over x, that goes off to 0. The limit as x approaches infinity of 1 is 1, and the limit as x approaches infinity of 4 over x squared, that goes off to 0. But this first part, 5 times a number that gets increasingly large, and it's in the numerator of the fraction, that goes off to infinity. So this whole value goes off to infinity. So its limit actually doesn't exist. It's unbound. Its end behavior, as you look forever right on this curve, would be the y values going off to positive infinity. How about the second one of these examples? Well, here I want to divide top and bottom by the highest power in the denominator, but the denominator has a radical, a square root of an expression. Now I just want to get the idea of what the overall effect of the power would be, and it's a square under a square root. So that would be where my overall effect of my power is like to the first power. But I have to be careful. Now you have to pay close attention to whether your x is going off to positive infinity or negative infinity when you're looking at your simplification of your square roots or even indexed roots. Now I know, and just kind of thinking back, that if my x's are greater than or equal to 0, the square root of x squared will be x, the same number I put in. So if I pick a number that is not negative and I square it and then square root it, I get right back to the value that I started with. And if I'm having my limit as x approaches infinity, they're positive numbers. It's going off to positive infinity. So this is the case that we have. Now if the square root of x squared is equal to x, then 1 over the square root of x squared is the same as 1 over x. And then that also means that if I take 1 over x and I divide it by 1 over the square root of x squared, as long as my x is not equal to 0, and it won't be because we're taking x's that are off to positive infinity, this is just a number divided by itself. And if you have a number divided by itself, that is just the value 1. So I can take this original expression and do the limit as x approaches infinity of 1 over x over 1 over the square root of x squared times this original function, the 3x plus 2 over the square root of 5x squared plus 7. I'm just building this fraction by a factor of 1 so that I get the simplification to be able to evaluate the limit. So now when you distribute that, it's the limit as x approaches infinity of, well, 1 over x times 3x over 1 gives me 3, plus 1 over x times 2 over 1 gives me 2 over x, over And then multiplying with radicals, I have the square root of 5x squared plus 7 over the square root of x squared. So I can actually write that as the square root of 5x squared plus 7 over x squared. So that gives me the limit as x approaches infinity of 3 plus 2 over x over the square root of 5 plus 7 over x squared. And now I can use those building block limits as x approaches infinity or x approaches negative infinity on this resulting simplified expression. So the limit of a quotient is a quotient of the limits. And I have the limit as x approaches infinity of 3 is 3, plus the limit as x approaches infinity of 2 over x, that goes to 0, divided by the square root of limit as x approaches infinity of 5 is 5, plus the limit as x approaches infinity of 7 over x squared goes off to 0. So I get 3 over the square root of 5, and when you rationalize that, you'll get 3 times the square root of 5 over 5. So this limit is 3 times the square root of 5 over 5, and I'll write it right in here. Now here's the tricky part. If I have an x that's negative, so if I have an x that is a negative value, x less than 0, then the square root of x squared is not x. The square root of x squared is the opposite of x. So if you're taking an x value that's negative, let's take negative 3. So if I were to plug negative 3 in for the x, in this expression where we talked about it earlier, so let's look at the square root of x squared, and then what that would be equal to in a simplified form. Well, if I take negative 3 quantity squared is positive 9. The square root of positive 9 is positive 3. But I plugged in negative 3. So I'm not getting out exactly what I plugged in. I'm getting out the opposite of what I plugged in. So I'm getting out the opposite of what I plugged in when I plug in a number that's negative in this simplification. Root, and my x goes off to negative infinity. So then working this through, we're going to bring it down a little bit here. That's the limit as x approaches negative infinity of negative 1 over x multiplied through the 3x plus 2 and 1 over the square root of x squared multiplied to the square root of 5x squared plus 7. I have the limit as x approaches negative infinity of negative 3 minus 2 over x over, and then remember that's going to be the square root of 5x squared plus 7 over x squared. So that gives me the limit as x approaches negative infinity of negative 3 minus 2 over x over the square root of 5 plus 7 over x squared. And then as x approaches negative infinity, my numerator is going to be negative 3 minus 0, or negative 3. My denominator is going to be the square root of 5 plus 0, or the square root of 5. And so when we rationalize that, we're going to get negative 3 times the square root of 5 all over 5. So I took the limit of the same expression in both of these. It's just that the first one we went to as x approaches positive infinity of that expression, and then the second one was the limit as x approaches negative infinity of that expression. So here's a case of a function that actually has a different horizontal asymptote as you look for your x's that are going forever right than when you're looking at the x's going forever left. So this has our end behavior that as x approaches infinity, as you look forever right, the function values would approach the horizontal asymptote 3 square root of 5 over 5. But then if you look at forever left, the outputs of this function would approach the horizontal asymptote of negative 3 square roots of 5 over 5.